plunger cylinder clearance. So I said that plunger and cylinder there is no much clearance, but actually there will be clearance. Why? Plunger is here, okay, and it is having some, let's say, valve seat like this. Yes, this is cylinder barrel, and I have one plunger like this, like this, and there is one ball, there is one ball. Okay, now in between this area, clearance area. So if you have clearance, that means there will be leakage. When piston is trying to move up, so what will happen? This TV closed and SV opens, right? SV opened when piston is trying to moving up. When trying to moving up, if that means this the pressure above the piston or plunger is very high, then your cylinder, okay, because you are lifting fluid, whole column weight is there on over your plunger, and you are lifting the plunger. Now, and this area, cylinder area, this cylinder area pressure is very low, because pressure difference is very high above the plunger, okay. I think P tubing I said, okay. So P tubing, P cylinder pressure difference very high, because the high pressure actually fluid will try to go back to this area, okay. And if a very high viscosity, then because of thickness, because of high viscosity, fluid will not be leaking back to the cylinder. Or if a very low clearance, then it will be helpful, but because of mechanical reason, you have to give some clearance so that piston movement will be very easy and smooth. So for that we have one formula how to calculate leakage rate. Actual flow rate we have calculated, APLS, right? Volume of the cylinder plus per second how many times it is traveling. So that way we calculated the volume. So that is called theoretical volume, but practically because of leakage your volume will be lower. Okay, what is the leakage formula? Leakage formula is like this: QL equals pi D or dP. Okay, pi D means diameter of plunger diameter, pi D del P and dC cube divided by mu L into some conversion factor 2.32 into 10 power minus 7. Many authors have written different types of formula, but in one book it is given as one formula. So for our calculation we will be using only one formula, because there will be so many choices. We are not going for many choices, but rather let's fix on formula, and based on that we try to calculate theoretical how much head you are getting, or pressure you are developing, or flow rate you are developing, and ideal condition how much you are developing, and the basis of that you can calculate volumetric flow rate from your pump. Okay, so what is pi? Pi, you know, 3.14 is constant, and D is a plunger diameter. D is plunger diameter. Plunger dia in it is given in inch, I think it is inch. Del P is the pressure difference between cylinder and tube. P tube minus P cylinder. Okay, this pressure will be very high actually. And mu is a viscosity in Cp, and L is the length of plunger. Length of plunger. This is inch. And one more, DC. DC is the clearance. Clearance, how much clearance? Plunger, this is barrel inner diameter D, plunger diameter, outer diameter small d. So DC will be capital D minus small d divided by 2. Okay, this is the clearance. How much small gap is there in between? Diameter, okay, I think divided by 2 will not be there. So this is diameter clearance, D minus D. Okay. Now from this formula we can see if plunger diameter is higher, QL proportional to D proportional to del P proportional to DC cube inversely proportional to mu inversely proportional to L. Okay, other things are constant. Now if I increase D, if I increase diameter, QL increasing, if I increase del P, QL increasing, DC clearance if I increasing, then it will be power Q. If I make double clearance value double, it will be 8 times more leakage, and viscosity inversely proportional. L, if I increase L or plunger length, it will be inversely proportional. How plunger length is affected? So normally plunger no need to make very big, but oil industry they will be using like 3 feet 4 feet also. Why they make very long instead of like maybe few inches? Because they want to increase the L. If L is longer, your Q leakage flow rate will be lower. Okay. So let's solve one problem. Problem is given here. D equals, okay, D is given 2.5 inch, del P is given 2000 psi, and diametral clearance also given 0.003 inch, L equals 48 inch, N is given 15 SPM, stroke length is given 48, mu is given 3 Cp. Okay. So using this formula, if we calculate Q equals pi into 2.25, okay, here one thing, by 2.25, it should be 2.25, yeah, 2.25 into 2000 into DC 0.003 power cube, mu viscosity 3, L is given, I think L is 48 inch, and constant 2.32 into 10 power minus 7. This gives 11.43 C inch cube per minute. Okay. So this cubic inch of volume it is delivering. Now if you want to compare with your barrel per day, then you have to convert, then you have to know the conversion factor inch and barrel, and you can use it. Okay. Now you got this one, leakage flow rate, Q or QL, whatever you write. Okay. And theoretical flow rate already we have got A, P, L and stroke length. Okay. So if we get this theoretical flow rate and leakage flow rate, then we can get volume efficiency, eta volume or volumetric efficiency or EV, whatever you write. Theoretical Q theoretical minus Q leakage divided by Q theoretical. So it will be your volumetric flow rate. Okay. Now if I give different clearance or different pressure or anything, so you should be able to calculate using this formula. Okay, so another formula is, problem is given here, so student can solve. Slippage you have to calculate for different clearance values, different stroke length and different flow rates. Okay, so as we have solved previous problem, similar way you have to solve here also. Gas interference. So whenever you are using sucker rod pump or reciprocating pump or any type of artificial lift, it will face liquid like water and oil plus gas plus sand. If you are lucky enough, then sand will not be there, gas will not be there, you will get completely liquid, that is fine. But completely liquid, when you are getting, you have to see whether you are getting very high water cut or not, because you have to make finally economical system. So if you want to make economical or benefit, you want to get monetary benefit, so you have to get less water, more oil or gas, less sand. Okay, so you are getting more sand, you have to handle properly, you have to get, you are getting more water, you have to handle properly, and you have to say check economy, how much benefit you are getting from your wellbore. Now if you are getting gas is good, okay, you can sell, but if gas is there and it is interfering your pumping operation, then neither you are getting gas nor liquid. So why? the gas is problem. You have piston, cylinder or plunger and barrel assembly. Okay. Now instead of liquid, this filled liquid partially and remaining gas. Okay, this area liquid, this is gas. What will happen? So you can remember this diagram. Okay, the indicator diagram. If you have completely liquid, life is beautiful, you are getting ideal curve, but practically the curve will be little bit distorted. We already discussed like this. Okay, but if you have gas during suction stroke, what will happen? During suction stroke, gas will be expanding. Okay, when gas is getting expanded, this gas, what will happen? Let's say you are creating low pressure because plunger is moving up, and P cylinder area, this area, this area pressure must be lower. Okay, pressure is lower, plunger moving up, and wellbore pressure. So wellbore pressure is higher, cylinder pressure lower, so wellbore fluid will be entering to this one. But if you have gas, what will happen? Initially gas will be getting expanded. Okay, when gas is getting expanded, so wellbore pressure and cylinder pressure difference will be lower actually. If you have liquid, then pressure difference will be higher. When pressure difference is lower, so your that cylinder area will not be filled with liquid. Okay, that's a half filled. When plunger is moving down, half filled liquid, so gas part will be initially compressed. Okay, then compression done, then liquid will be entering to your TV and it will go up. So gas will be compressing, decompressing continuously actually. When plunger is moving down, it will be getting compressed. Okay, then fluid will be going to your TV and upside. When plunger is moving up, so that time gas will be expanding, so the whole cylinder area will not be filled. So whatever formula you have used for volume flow rate or PD, whatever you say, APL, so that formula you use, right? Area of plunger into stroke length. Now stroke length means we assume that whole stroke will be filled with liquid. Okay. Now you don't have whole thing filled with liquid, so partially filled. Again gas is getting expanded, contracted. Because of that your volume flow rate will be lower. Okay, sucker rod pump can face volume flow rate 70, 80%, 90%. Okay, and if you have 80%, still you can run your sucker rod pump. But if you have less than 60%, if you run a sucker rod pump, then maybe you will not get any flow. Okay, this condition is called gas lock. Gas lock means cylinder is filled with gas and your piston is moving up and down, piston or plunger. Okay, plunger is moving up and down, cylinder filled with gas, so gas expanding, contracting, expanding, contracting, expanding, contracting. When you are getting expansion and contraction, actually you are not pumping liquid. Your main purpose was to pump liquid only. So that means your system working, you are giving energy, electrical energy, everything, but you are not pumping. So you are not pumping, that means your economical loss will be there. So I was discussing with some engineer, so they say like if such situation is there, gas lock is there, so you have to switch off the pump, you have to allow leakage. Leakage where? Already we calculated leakage through the plunger and barrel, there will be some small gap. Okay, travelling valve also there might be some gap. Okay, and you stop the pump and you allow some leakage so that the cylinder cavity will fill with liquid and gas can escape. So that way, and that stoppage can be several days actually. Okay, so normally the production engineer, they will be avoiding gas lock, so they will be making certain mechanisms so that gas lock cannot appear. Okay, we will discuss later how to avoid it. So one is gas lock problem, another problem is in the title you say fluid pound. What is fluid pound? Okay, I have liquid, I have some portion, almost a very low pressure gas may be there. Okay, and when piston is moving down, moving up, so what you are doing, liquid will be entering into the cylinder area. Okay, and cylinder area some portion liquid is there and maximum portion gas, and when piston or plunger is moving down, what is happening? When plunger is moving down, because of its fluid load and wet load, its speed will be higher. When it is moving up, speed will be lower. Okay, when it is moving down, speed is very high. At high speed, when piston or plunger is hitting the liquid surface, so this should create lots of vibration. Okay, because of vibration, the rod can buckle. Okay, this is because of fluid pounding, rod will buckle. What is happening? Rod and whole mass is moving at very high rate. Suddenly you are stopping the plunger end. Okay, so what happened? Plunger is hitting this one, and the whole pressure pulse or whole vibration is not shifted to the top. Only bottom portion got stopped and top portion is still under motion. What will happen? Whole motion, this is stopped, so you are creating certain pressure. Okay, compressive force. When compressive force is there, it will be buckling load. So I will discuss later failure mode. One failure mode is there because of tensile, rod will fail. Another failure mode is there, buckling. Buckling means very long rod is there, very thin long rod, and you are applying pressure. So the rod will create buckling, or it will bend like this. Okay, when it is bending like this, this rod will be touching your tubing. It will create friction, and the joints, rods will be long of 25 feet, 30 feet, and there will be one joint coupling. Okay, one rod couple, another rod couple, another. So 25-30 feet long rod coupled, you are making 1 kilometer, 2 kilometer long rod. Okay, the coupling will be failed. The rod will be rubbing your tubing. Again, it will be a problem. So when there is any fluid pound, your system can fail immediately. Vibration and rod failure can occur. So you have to avoid fluid pound and gas lock. Okay, so this phenomena is called gas interference or fluid pounding. So sucker rod pump, when you have gassy oil, gassy wellbore, very high amount of gas is there, or you are creating two-phase flow when pump intake is happening. Okay, because of this bubble point line is crossing, and if two-phase flow you are creating, that in that case gas will be coming, again your gas lock or fluid pound can occur, then pump can fail, or maybe production can be stopped. So you have to avoid this fluid pound or gas interference or gas lock phenomena. Okay, so you have gas inside your wellbore and you have to avoid it. How to avoid? So there are basically 3 techniques. There may be some other techniques also available. So first discuss about these 3 techniques. One is that you have casing, okay, and perforations are here, and your barrel is here, your plunger is here. Okay, now what happens? Oil and gas will enter here. Okay, and if you have gas, so gas also can enter here. So this will give your gas lock. If oil and gas entering, it will passing through traveling valve. This is standing valve, this is TV, passing through standing valve, that cavity, then you have problem. So what you have to do? You have to avoid that gas part. How to do it? So natural gas anchoring is that they suggest that place your pump intake area below the perforations. So what they do? This is your perforations area. Okay, this is your reservoir maybe. Okay, and you drill further and put your pump intake here. Okay, and your plunger here. Okay, so what happens in this case? Your perforations are here. Okay, fluid will be entering from here, oil plus gas maybe. Assume this oil and gas is there. Okay, so what will happen? The gas will be escaping through this area. Okay, this is tubing. Okay, through tubing you have inserted all these things. Okay, and liquid will be falling down and will be collected here. Okay, so liquid will be entering only, and gas will be escaping through the annulus. So gas, natural gas gas anchor. So what will happen? Natural gas anchor, gas will escape through annulus. Okay, and liquid, because of high density, it will fall down, it will enters pump. Okay, so naturally you are separating, just pump the pump intake below the perforation. So oil and gas entering, gas will be going up because lightweight, heavy weight or high density fluid will be coming down and it will be entering into your pump, and in that way you are separating gas. So it is very simple. Another poor boy gas anchor, there is also similar mechanism. Actually they will have separate one instrument like this, and when lots of pores will be there, okay, and your pump intake is here, okay, so gas, oil will be coming like this, or liquid will be coming like this, gas will be escaping. Okay, so pump will have your travelling valve, standing valve, all this mechanism will be there, right? Okay, so poor boy gas mechanism also is similar to natural gas anchoring system. So in perforation area you put this instrument, poor boy gas separator system, and it will separate, like gas will be going up and your liquid will be going down and it will enter into your pump. Okay, another is Packard type gas anchor. In this case actually you put separate path for gas escaping and liquid entering, so that is less commonly used. Basically natural gas anchor is used everywhere. It is very simple to use, just put pump below the perforations, that is the simple, a few feet below the perforations. Again your wellbore pressure or intake pressure of pump should be higher, so that it will be assisting travelling valve to standing valve to open. If pressure is very low and you are creating vacuum, when plunger is moving up, your inlet pressure is not sufficient, so in that case pressure will be very low. When pressure is very low inside cylinder or wellbore, so two phase flow can be created, so that can create gas also. Although you have created already natural gas anchor, pour, whatever things are there, gas mechanism, still because of low pressure creation, some gas will be coming out from the liquid because of improper design. So in that case again gas lock or fluid bound can occur. So you have to know the reservoir fluid properties also whenever you are designing all this system, whole system. Okay, so one way you have used gas anchor system to avoid gas. Okay, you had gas problem, so you use gas anchor system, but still there is gas. Now what will do? So there are several companies there and several patents are there. In the, if you search patent, you will find lots of anti-gas lock designs. Okay, gas lock breaker you can say, and some are in patent, some company producing some anti-gas lock mechanism. I'll explain this research or this comparative history I have done myself, and I published one paper actually some time back. So students also can try to find some more design if new design is available, and comparative analysis also they can do and see which will be better. Even they can find new idea also for anti-gas lock mechanism. So first one, you see this top picture. Top picture shows it is having barrel, one travelling standing valve, one valve cage, one plunger, one travelling valve. When it is moving down, the travelling valve will be opening path and there will be some holes here. So fluid will be entering and it will go up like this. Okay. This is downstroke. When piston or plunger is moving down, so this is closed, travelling valve is closed, standing valve is opening. Okay, this is upstroke. Okay, when plunger is moving up, bottom valve or standing valve is opened, travelling valve closed, so fluid entering into the cavity. Okay, when plunger moving down, bottom closed, TV open, fluid going up the plunger. In that way you are delivering fluid. Now if I have gas, so gas will be filled this cavity area. Okay, this cavity area. So if gas is filled, then you have problem, you have to solve it. How to solve it? So there are several techniques are available. I will explain two techniques. One technique is that one takes the variable slippage pump. One company, I think they are manufacturing variable slippage pump. What is variable slippage pump? This is standing valve, and I have one traveling valve like this. Okay. So if this area is filled with gas, okay, this area filled with gas, what will happen? This area filled with gas and plunger is moving up. Move plunger so high so that your this pressure A, I'll put name B. Okay. So fluid from A will be entering to B, because you are giving actually larger leakage. When plunger and your barrel, if properly designed, there will be no gap in between. Actually, small clearance will be there, but not significant. But if you are giving variable slippage, means you are enlarging barrel size enlarged. So plunger, when it is moving up at after a certain level, so that time this clearance is too high. Okay, the plunger and barrel area clearance is too high. Okay, this clearance area, clearance is too high. When clearance is too high, leakage will be very high. QL formula you have seen, right? QL proportional to DCQ, clearance power Q. So you are intentionally making larger clearance. So larger clearance means gas at B location will be escaping and it will be reaching to A, and A liquid will be slowly moving down. When A liquid is slowly moving down, what will happen? Gas gun, your chamber is filled with, or B area is filled with liquid, done, life is beautiful, there is no gas lock. Okay, but what you are doing, the full stroke you are not getting production actually. So every stroke you are getting certain amount of leakage, so your volume flow rate will get reduced, but you will not face any gas lock. Okay, if you want to get 100% fluid flow rate, AL area into length of the stroke, okay, number of stroke into number of stroke, that volume, if you calculate, that is theoretical flow rate. But here, because of this, you are getting extra leakage, extra DC is there, that's why you are getting lower flow rate. Every stroke you are getting lower flow rate, but your problem is solved, no gas lock. So problem free operation, but take little bit lower. Okay, so that's why the company is doing their marketing. Another concept is there, mechanical plunger pin. So mechanical plunger pin is like this. Okay, I have one valve cage, I put one pin, and when I have plunger, when plunger is moving down, plunger pin is like this. Okay, standing valve cage is having one pin like this. Cage is having one pin. When plunger coming down, the traveling valve ball will be hit by this pin. So forcefully this will be unseated, the ball will be shifting from its own sitting position. When sitting position is gone, so it will create lots of leakage. Okay, so I'll draw another picture, another figure here. Let's say this is the condition, and okay, when plunger at the bottommost position, you can see because of this pin, ball is shifted or lifted up, and because of that lifting up, all the gas will be making one path, it will go up. Okay, so every stroke, when plunger is coming to the nearby bottom, you are giving some pin, something unseating of the ball every time. Okay, so every time small amount of liquid also will be leaking out, but gas will go out. So they are saying as mechanical plunger pin. Okay, and every stroke we are doing, so gas will not get accumulated, they are saying. This is one technique. Another technique is that gas vent pump. Gas vent pump, they have given name, is like this. Okay, plunger is here. Okay, there is one gap. Okay, there is one gap. When piston is or plunger is moving up, so when it will be crossing this gap, sorry, there is a gap. Okay, there is a gap and there is a piston. When there is a gap, plunger is moved above the gap, so that time gas will escape and liquid will enter from the gap. They are saying gas vent pump. So whatever gas is accumulated in the B area or cylinder area, the gas will be vented out and liquid can enter. So that gas lock will go. So again, every stroke you have to lose certain amount of fluid. So your volumetric flow rate will be little bit reduced, but you will be avoiding gas lock or fluid bound. So similarly, other designs also available. So just you can discuss, and I prepared some comparative analysis also. So just you can go through other designs. I explained the key designs. Okay, so this is done by me actually. So you can study and you can see whether if there is any more addition you have to do. So gas lock breaker, several gas lock breaker technologies available. Some in the form of patent. Some company has produced product also. So one 2-valve plunger, gradually enlarging plunger, gas vent pump, gas compression chamber, mechanical plunger pump, top valve pump. So what will the positive negative aspect? I made myself and I wrote in this paper. So students are suggested to go through this paper, and you can add more points also, or you can delete some points also. Okay. Pump off control. Pump off control. Now you know that your sucker pump is having gas. Okay, you have gas anchoring system, but still gas coming. Now you change your bottom assembly with newer type anti-gas lock system. Now your engineer saying, sir, still not working. You have to do some pump off control. Pump off control means there is no fillage of your cavity or cylinder. Okay, because low amount of liquid is coming, or low amount of liquid is coming, that's why it is filling with gas. So if it is filling with gas, it will be multiple problem. So what you do, you switch off the pump for certain time, one option. Second option is that you reduce the pumping rate. Let's say your liquid is coming, let's say 5 barrel per day. Okay, your pumping rate is 10 barrel per day. That means 5 barrel is shortage is there. Okay, so if you are to pump 10 barrel and you have only 5 barrel, what will the pump will do? It will get some gas. Okay, when it is pumping without liquid, it will be creating some gas. So gas will be a problem. So in that case, you switch off the pump for certain time, or you reduce the pumping stroke. Okay, so design flow rate, the formula they have given like maximum inflow capacity 24 per day, pump volumetric efficiency, how many hours you are running the pump. So here one problem is that gas fuel maximum flow rate 300 barrel per day. Again, I am writing small b, small d. So small b, small d. So I don't know. They most probably they have not created some standard unit. That's why many books are writing different ways. Okay, and SRP is being used for what rate the pump should work. Okay, so volumetric efficiency 80%. So design flow rate is 324 into 0.822. So 450 barrel per day. Okay. So if you are running for 20 hours, then things will be okay. But if you want to run for 24 hours, let's get more production. So finally, it will not give you more production, or that will create a problem. These days, variable frequency drive also there. Using variable frequency drive, actually you can change electrical frequency. Electrical frequency will change your motor frequency. The motor frequency further will reduce your gearbox speed. So gearbox speed means your whole SPM or stroke per minute will be reduced. When you are changing stroke per minute, still fine. Then how to know that your pump is getting filled by gas 80%, volumetric 70%? So you have to study your pump curve or dynamometer curve. So using that one, actually you guess how much volume of gas is there, if there is any problem in the well bore. So using that analysis you can do. In the next lecture, actually you can analyze that.